All right, so radicals. Let's get all those Chromebooks closed up. You closing that up, Jalen? You in the process? Oh, there you go. Okay. So simplifying radicals. Remember, our goal when we're simplifying radicals is always to get as much outside of the radical as we can, right? One thing that's helpful when we're doing problems like really big like that. I mean, what if we had to simplify the square root of, you're going to do this one pretty soon. You have to simplify the square root of 3,456, right? So part of that process is going to be, you're going to have to make a factor tree and factor that number completely. So one thing that's very helpful, you can use a calculator for that, but you don't want to have to just sit there and keep randomly trying numbers in the calculator to see what divides into that radicand. So it's helpful to have some little tricks for knowing numbers that divide evenly into big numbers, right? What are the factors? What are some of the factors of 3,456? So here's how you can tell. There are some rules that are really simple, and I'll make sure, gosh, I haven't printed this out yet. I'll print this out, but I'll put it in the Google Classroom in the handouts part. Okay, and then you can just access it anytime you want to. But here are some good just divisibility rules. How do you know if a big number is divisible by 2? Easy, if it's even. If it's even, it's divisible by 2, okay? How do you know if a number is divisible by 3? Well, if you add up all the digits of the number, and if the sum of the digits is divisible by 3, then the whole number is divisible by 3. So for example, here we have a huge number, 11,274. How would you know if that's divisible by 3? Well, if you add up the digits, 1 plus 1 plus 2 plus 7 plus 4 is 15, right? And 15 is divisible by 3. So the whole number is divisible by 3. Make sense? Okay. How do you know if a number is divisible? I'm going to skip down here. Is divisible by 6? Well, if it meets both of those rules. If it's divisible by 2 and divisible by 3, then it's divisible by 6. So a number is divisible by 6 if the sum of its digits is divisible by 3 and it's even. Okay, make sense? Right? How do you know if a number is divisible by 9? Same rule as if it's divisible by 3. You add up the digits, and if the sum of the digits is divisible by 9, then the whole number is divisible by 9. So for example, if I add those up, 3 plus 7 plus 1 plus 4 plus 3 is 18. If I add up all those digits, 18 is divisible by 9, and so that great big number is divisible by 9. Okay? Some other ones, some simple ones. How do I know if a number is divisible by 5? Well, if it ends in 0 or 5. You guys know that one, right? How do you know if a number is divisible by 10? If it ends in 0. Okay, and then the last two we're going to cover are 4 and 8. These are kind of cool little tricks. A big number is divisible by 4 if, whoops, I have this messed up. There, that's better. A big number is divisible by 4 if the last two digits are divisible by 4. So I could take this enormous number, 47,108, and the last two digits are just 8, right? Because 8 is divisible by 4, the whole thing is divisible by 4. And then you have a similar rule for 8s. If you have a really big number, if the final 3 digits are divisible by 8, then the whole big number is divisible by 8. So 313,072, because the last 3 digits are just 72, because 72 is divisible by 8, the whole thing is, okay? And then the one for 7, I'm not even going to mess with that. That one's so convoluted and complicated, it's not even worth it. Just check that one on a calculator. So there's some rules, some quick, easy rules to help you know if a big, what numbers divide into a great big number, okay? Why are we doing that? Well, the reason we're doing that is because our goal is going to be able to simplify large radicals when the number is really big under the radical. So first thing we do, like let's take this example. I've got a 2 out front already, so that we just leave alone. But I've got to simplify the square root of 26,460. So we would have to take that 26,460 and make a factor tree out of that. Well, what's a number that divides into that, obviously? Did I put it? Oh, I did. You're right. Yeah, what's one obvious number that divides into that? 10, right? Because I got ends in a 0. And 2 does also, you're right. But we're better off picking slightly bigger numbers so our tree gets more spread out and doesn't get so super long, right? So if we break this thing up into 10, and then I'm just going to get what? 2,646. 10 splits into 2 and 5. And those are prime, so I can circle them. Whoops, I can't read that. So I'll circle those. They're done. Those branches are done. What about 2,646? Stare at that for a second. See if you can remember some of my tricks. Well, 10 can't divide into that because it doesn't end in 0. But so 3 does. How'd you get that?
Because 3 can go in this case.
Well, it's not. You have to add up all the digits for 3. So 2 plus 6 is 8 plus 4 plus 6. That adds up to 18. Right? Oh, so 9. Yeah, there you go. So 9 divides into that because the sum of the digits is 18, which is divisible by 9. So 9 divides into that. Everybody see that? So we'll break this one up to 9 and what? 9, I'd have to divide 2,646 by 9. I'll show you a trick for doing that, by the way. If you have single digit numbers, you can divide them into a big number just using kind of like a shorthand long division. Does 9 go into 2? Does it go into 26? Well, how many times does it go into 26? No, 2. It goes in 2 with how many left over?
1.
No. 2 times 9 is 18. 8. So I have 8 left over. So now we move on to the next digit, and I carried an 8 over. 9 goes into 84 how many times?
8.
9, right? 9 times 9 is 81, so it goes in 9 times with how many left over? 3. And 9 goes into 36 how many times?
4.
So there you go. Okay. 9 breaks up into, okay, and those are done. What about 294? So 3 does, doesn't it? Because look, 2 plus 9 plus 4 is 15, which is divisible by 3, right? It's also even. So what would go into it if it's even? 6 does, right? If the sum of the digits is divisible by 3 and it's even, then we know 6 goes into it. So we could break off a 6. Well, let's see. 6 goes into 29 how many times? 6 goes into 29 how many times?
4 times.
4 times. With how many left over?
9.
No. Oh, you're right, yeah. Yeah, you're right, sorry. Huh. You're right, 5. 6 goes into 54 how many times? 9, there you go, okay. And, oh, that 6 shouldn't have a circle around it. It's not done. We didn't hit the end of the road on that 6. 6 breaks up into what?
2 and 3.
There you go. 2 and 3, and those are done. And the 49 breaks up into 7 and 7. And those are prime, so I can put circles around those. So we got this thing completely factored. What do you do next? Okay, now, and this is really important. Don't skip this step. Now we're going to write the product of all those factors in order from smallest to biggest, right? So let's see, the smallest factor we have is 2. How many 2's do we have? 1, 2. Okay, so I'm going to put, I get 2 2's under my square root. How many 3's? Now I'm going to have to multiply by all the 3's. 1, 2, 3 3's. So I get my 3 3's. I get 1 5, and I get 2 7's, and I'll just cross them off as I go. So there's There's the product of all the factors in increasing order, right? Okay, here's the trick. The trick is called couples go out, singles stay in. So if we're doing a square root where have you guys learned this one before? So if what's the number that sits on the radical this time? If it's a square root, it's a 2. So the index number is 2. So that's telling us how big the groups are that go out of the radical. So group of 2 is a couple, right? Couples go out, singles stay in. So then I'm just going to take all of those factors and I'm going to see how many couples there are in that list, right? So you guys tell me, how many couples are there? How many? What are the couples? 2 and 3 and 7. You're right. Yeah. Look, I've got a total of 2. So I have a couple of 2s. I have a couple of 3s, and I also have then a single 3, a 3 that's left over. I have a single 5, and I have a couple of 7s. Okay, so why do couples go out? Well, what is 2 times 2? What's the square root of 4? 2. Oh, what do you know? So the square root that goes with that couple of 2s is going to end up being a 2 outside the radical, right? 3 times 3 is 9. The square root of 9 is 3. So look, that gives me a 3 outside the radical, okay? So what's the rule then? For every couple that I have inside the radical, I'm going to get a single number outside the radical. Everybody see that? Singles stay in. So the 3 and the 5 stay inside the radical. Okay? Everybody look at that. Does that make sense? Yeah. Don't make the mistake of thinking because I have a couple of 3s that I get 2 3s outside. I don't. I only get one number outside for every couple that's inside. Okay? And then all I have to do is just multiply the outside numbers together. Well, I already had a 2 out front. I got a couple of 2s, couple of 3s, and a couple of 7s, so I got 3 other numbers that are multiplied out front for a total of what? 2 times 2 is 4 times 21 is 84, right? I get 84 outside, and inside I get 3 times 5 equals 15. Okay, make sense? Okay, try it. Go, try that one on the board. So, yeah, you bet. So that looked great. One thing, don't skip this step though, because this is really a helpful one, right? So now once, you can always kind of set up the template where you got outside stuff and inside stuff. And then you're just going to put put everything in its rightful place here. Once I get the string of factors all written out, because this is a square root, we're looking for couples. So there's a couple, there's a couple, there's a couple, there's a couple, right? And so what do we get outside? Well, we're going to get all these couples become outside numbers, 2 times 2 times 2 times 3, and the singles become the inside numbers, and we got it, right? So those multiply to 24, and the inside numbers multiply to 6. And we got it, right? Okay, now the nice thing about this is we can extend this. This isn't just for square roots. We can do this for cube roots or fourth roots or whatever. It just depends what kind of root we're talking about. The number on the radical determines the kind of root, and it determines what stays in. If this is a cube root, well then 3 of a kind, so triples are going to stay in, and everything else, triples are going to go out, and everything else is going to stay in, right? So what's that mean? Triples go out, and everything else would be all the singles and the couples would stay inside the radical. So for this one, let's do this one together. Our radicand is 21,600. Let's factor that and take all the triples out and leave everything else inside. So what's an obvious big number that goes into that? 100, because I've got 2 zeros. Good. So we could break this up into 100 and 216, right? How do I know what's left when I divide it by 100? I just get rid of those 2 zeros, right? 100 obviously breaks into what? 10 and 10. And each of those 10s breaks up into a 2 and a 5, right? How about 216? What goes into 216?
3.
I could even do bigger. Okay, something even bigger. 9. Because 2 plus 1 plus 6 is 9. The sum of the digits is 9, which is divisible by 9. Okay, so we could do that. So we could break this into 9 and what? Well, 9 goes into 21 2 times with 3 left over. 9 goes into 36 4 times, right? So I get another 3 and 3. And how about 24?
8 and 3.
8 and 3. And 8 breaks up into 2 and 4, right? Okay, so that's going to give me a 2 and a 4, which breaks up into yet another 2 and 2. So wow, I got lots of stuff there. So we get then the cube root of, let's cross these off as we go. How many 2's? 1, 2, 3, 4, 5. Okay, how about 3's?
1, 2, 3.
3. Okay.
4.
You see a 4?
Yeah. I see a 4 right there.
There's only 3 3's though, right?
Yeah.
Okay. And then 2 5's, and that's it, right?
Yep.
Okay. So we got to figure out what goes outside our cube root and what goes inside. So what are we looking for here? How big are groups?
3.
Triples. I've got a triple 2 and a triple 3, and that's it, right? So outside I'm going to get a 2 times 3. Inside I'm going to get everything else. So all that stuff, that couple stays inside, right? Inside I'm going to get a 2 times 2 times 5 times 5. And then I just have to multiply those numbers out and I'm done. There shouldn't have been a 4. Even that one right there, you mean? It wasn't the end of the line, so it doesn't count. We only picked the prime factors at the end, right? So then outside we get a 6. Inside we're going to get 10 times 10, right? 100. Okay, give me thumbs on that. Everybody good with that trick? Great trick, huh? Okay, the other thing I wanted to show you today is another awesome trick. This makes this stuff really simple. So what happens if we're taking a square root of a variable to a power? So a square root of a power, or any kind of a root, a radical with a power in it, like the cube root of x to the 11th. How are we going to simplify that? There's a really good little shortcut here. What you can do is you can write the radical, write that root as a fractional exponent. So remember from what, yesterday, day before, I can't remember what day it was, the 3 on the radical, the index is 3. That goes in the denominator, and the 11 goes in the numerator, right? So this is equivalent to, this radical is equal to x to the 11/3 if I write it as a fractional exponent. So all you have to do is take that fractional exponent and write it as a mixed number. So 11/3 is what as a mixed number? Let's think how we do mixed numbers. It's been a while. 3 goes into 11 how many times? 3 times. With how many remaining? 2. So it goes in 3 times, and 2 is what remains over the denominator. The remainder is what remains over the denominator. So 11/3 is the same as 3 and 2/3, right? Okay. So what does that mean? Well, 3 and 2/3, really what 3 and 2/3 means is 3 plus an extra 2/3. So if I use my properties of exponents, I could split that into 2 separate powers. X to the 3rd times x to the 2/3 would equal x to the 3 plus 2/3. Because when we multiply like bases, we add the exponents. If that didn't make sense, or that you don't really even have to think of it that way, that's technically the way it works. And then I put the x to the 3rd out front, and the x to the 2/3 I turn into a radical. But you could stop right here. When you get the mixed number, you just know that the integer part, the whole number part of the mixed number, is the part that's going to go out front, right? So that's going to give me an x cubed outside of the radical. The fractional part represents the part that's in the radical. Now let's trace these parts. We know that the 3 in the denominator always just tells you what kind of root we're taking, right? And the 2 in the numerator tells you the power that's of that variable that's inside that radical. Anybody see that? Okay, so we know that if I have x to the 3 2/3, I'm getting x cubed outside, and inside my cube root, the numerator is a 2, so I'm going to be stuck with an x squared inside. Good? Give me thumbs on that. Does that make sense? Okay, prove it. Go try one. So, how do I write this? How do I write that as a fractional exponent? What would that be? 8/3, good. That's going to be x to the 8/3 power. If I write 8/3 as a mixed number, what's that going to be? Okay. X to the 2 and 2/3, right? There you go. So the whole number part is going to be the part that goes outside. So now we're just going to have an outside part and an inside part of our cube root, right? So the outside part is x squared, right? That's telling me the exponent that goes with x outside, and what goes inside? X squared, because the numerator tells me what's going to be the power that's inside my cube root, x squared. Okay, make sense? All right, so what we're going to look at, I guess not tomorrow, but we'll look at next week, what we're going to look at is how could we do this if we have, like, what if we had something like that? Yikes. What if I had the 4th root of 288 x to the 7th times y times z to the 18th? That looks terrible. What would my strategy be? Break it up. I'm just going to break it up into 4 separate parts. I'm going to break it up into the 4th root of 288, which we know how to do. We just make a factor tree. And if it's a 4th root, how big of groups go out? Yeah, quadruples would go out and everything else would stay in, right? And then I'm going to have a 4th root of x to the 7th, which just becomes x to the 7/4 times a 4th root of y to the 1. That's just y to the 1/4. And then I get a z to the 18th, so we're going to multiply that by the 4th root of z to the 18th, which is z to the 18/4, right? Everybody see that? And we'll just do that same stuff we've just been doing. We'll just do that 4 times separately and then combine everything in the end into one radical. Does that make sense? Okay. I'm going to pause there, though. We don't quite have enough time to do that today, but that's what we'll look at next time. Yeah, so please